In match problem 5, we took a longer route to get to our final solution of -6. In general, we have some other theorems that we've introduced, some other properties that are going to allow us to solve a problem like we had in match problem number 5 quite a bit faster. So what we want to do is look at how we can apply some of those quicker techniques, starting with match problem 6. So here what we have is the limit as x approaches -1 of x to the 4th minus 2x plus 3. This is a polynomial function. And according to that theorem we just established, again, the short version of that theorem is if we have a polynomial function, try direct substitution. So what we're going to do is take this value as x approaches -1 and just plug that into the function for every value of x. So this is going to be -1 to the 4th power minus 2 times -1 plus 3, which will give us 1. -2 times 1 will give us plus 2, plus 3, or 6 as our limit for that function as x approaches -1. So that was quite a bit faster than using the properties, breaking that limit across each of those individual terms. And since we have those theorems established, from this point on, we can use these faster approaches. So in part B, we have the square root of 3x squared minus 6 as our function. This is not a polynomial. However, if we go back to the properties of limits, we realize that we can bring that limit notation underneath the radical and write this as the square root of the limit as x approaches 2 of 3x squared minus 6. So initially, we didn't have a polynomial, but now when we look at 3x squared minus 6, that is a polynomial since we use those properties to rewrite our problem. So again, we can try direct substitution. So this is going to become 3 times 2 squared minus 6, and we still have that square root around this, making this the square root of 3 times 4 minus 6, or just the square root of 6. So pausing here just for a minute to mention this is our final answer for a problem like this. You could type the square root of 6 into your calculator. You would get some repeating decimal number. That would be the appropriate thing to do if we're dealing with application problems. So if your answer should be telling someone how many units they should be producing, how much money they can expect to make, you can't tell someone that you should expect to make the square root of $6 or something like that. So for application problems, we're going to want to use rounded numbers to give more context to our answers. But for these theoretical problems, the square root of 6 is our exact answer. So that's the form you would want to leave this in. So part C, what we have is not a polynomial function, but in this case we do have a rational function, x squared over x squared plus 1, since we have a polynomial divided by a polynomial. So again, we can try direct substitution, and what we have to make sure is that we don't end up with a 0 in the denominator. As long as we don't end up with a 0 in the denominator, we can solve this limit again by direct substitution. So this will be -2 squared divided by -2 squared plus 1. So that will give us 4 over 4 plus 1. And again, what we want to check is that here in the denominator, that's not equal to 0. Since that's not equal to 0, we can go ahead and conclude that our limit in this case is 4/5. In this section, all the problems we consider, you'll be able to solve this limit by direct substitution. Solve the limit of a rational function. In the next section, though, we'll look at cases where that denominator does equal 0 and what we have to do in those cases.